Hi everyone, in this video I'm going to be talking about the MgO Lab, magnesium oxide lab, more specifically calculating the empirical formula of magnesium oxide. So I'm going to go through the lab setup, lab precautions, and sample calculations. So a quick overview of the lab. You're going to be given a piece of magnesium and you're going to burn it in a Bunsen burner. And as you know from before, when you burn metals in the presence of oxygen, the oxygen is going to bond to those metals, forming some kind of metal oxide. In this case, it's going to be a magnesium oxide. And what we're looking to do is find the empirical formula, or the simplest ratio that it's going to form, that the magnesium and the oxide will form. Okay? Let's make sure we're clear on what empirical formulas are. Empirical formulas are the simplest ratio of elements in a compound. You've probably seen this example before with empirical formulas. By the way, this is not designed to be a from-scratch teaching of empirical formulas, so if you don't know what empirical formulas are, you want to go back and do a little bit of research. There's another video I have on it, there's textbook reading. But the basic idea is, in an empirical formula, it's the simplest ratio. So what's the simplest ratio of these elements? Well, 6, 12, and 6, it's 1, 2, and 1. And you don't write the ones, but this would be the empirical formula of this, and this of course is glucose. So the empirical formula, EF, is CH2O. The original formula, the actual formula, is called the molecular formula. So what we're trying to do today is find not the molecular formula, because of course molecular refers to covalent, and when you bond magnesium and oxygen it's going to be ionic, so you're actually not creating molecules. We're going to be finding an empirical formula. Let's review how we do that. Empirical formula problems are always presented to you in one of two ways. You're either given the mass of two or more elements, or you're given a percent composition. For example, let's say you were told you have 83% copper and 17% sulfur. I made these up on the spot. They probably don't actually work out to be anything meaningful. But the idea is you would assume it's a 100-gram sample. So it's as simple as literally going like this. 83 grams and 17 grams. Because you're just finding the proportion between the elements. And you're not looking for the mass proportion. You know, you're not going to say like, it's about 5 to 1 or so, or 6 to 1. You're going to be finding the molar proportion. You turn the grams into moles, look for a pattern. So let's go with this example. We'll solve it very quickly. All right, so we have 16.32 grams of chromium. And we're going to turn that into moles. The molar mass of chromium is 51.996 or 52.00. And remember, that's the molar mass, meaning it's the number of grams that equals 1 mole. Or in other words, 1 mole over 52.00 grams for chromium. Fluorine, 17.89 grams of fluorine, and the molar mass of fluorine is 19.00 grams. Now real quick, you might say, hold on, isn't fluorine one of those diatomic elements that always pairs up, or a Brinkelhoff? And yes it is, but that's only when it's like in its natural elemental state, when it's just a sample of fluorine not bonded to anything. Well, this is going to be fluorine bonded to chromium. So you're not going to double the molar mass and go with 38, you're going to keep it with 19. All right, and what we're going to do here is work the math out, find moles, and look for a pattern. So up here I got 0.313 moles of chromium, and down here I got 0.942 moles of fluorine. And you're going to look for a pattern. If you see the pattern, if it's obvious and if it's clear, then you're done. 0.313, 0.942, I can tell that's pretty much exactly 3 to 1. Now, if you aren't sure of the pattern, or if you want to confirm, you divide each of these by the smaller number. The smaller number is 0.313, 0.313. This is obviously going to now be 1, and this looks like about 3, 0.942 divided by 0.313. 3.01, so yes, it's about 3. So my empirical formula is 1 chromium, 3 fluorines, CrF3, which you can of course name as chromium 3 fluoride. So as you can see, all you need to solve an empirical formula problem is to get the mass of one element and the mass of the other element. And that's what we're going to do in the lab. We're going to take the mass of magnesium and find the mass of oxygen that bonds to it. I'm going to write that out because it's very simple. All we need to solve the MgO Lab, you simply need mass of Mg, mass of oxygen, I'll say that bonds to it. You do that, you can solve the lab. Let's talk about how we're going to do that. Let's take a look at the experimental setup here. So a few pieces of information you should know. Let's see if I can get this to not fall. Okay, so our Bunsen burner is obviously going to provide the flame we need. The magnesium is in the form of a ribbon. We call this magnesium ribbon. You can see it's a silver colored metal. It's a little dull on the outside. What we're going to do is take some sandpaper or steel wool and kind of strip the outside. And you could probably guess why it's a little dull, because magnesium, being an alkaline earth metal, is slightly reactive. It's the least reactive of them besides beryllium, and it's going to react very slowly with oxygen in the air over time. So we're going to remove that outer coating of magnesium oxide, produce fresh magnesium underneath so it can react very quickly with the Bunsen burner. Now I said it reacts slowly with oxygen. That's at room temperature. If you put in a Bunsen burner flame, well, now we're talking about an incredibly fast, nearly instant reaction. So you're going to take your magnesium and you're going to curl it into a little ball here. As you can see, your strip's going to be about 20 centimeters long, and you want to turn it into, kind of bend it over like this so you have a ball with a little bit of air in the middle. You don't want to like compress this thing until it's like super, super, super crushed. You want a little bit of air there. And you're going to find the mass of this. And notice right off the bat, you're halfway done with the lab, because all you need to solve the lab is the mass of the magnesium and the mass of the oxygen that bonds with it. Now, your teacher might have you find the mass of this in a couple of different ways. You can either just put it on the balance straight up, you can put it inside what's known as the crucible, or you might even do a density analysis where you're given the density of this, and you're going to get the length and go from there. So however you find the magnesium, the mass of the magnesium, that's what you're going to start with. Okay. Now we need to burn the magnesium and calculate how much oxygen bonds to it. And before we work out how we actually do that, let's figure what we can do for that. There we go. So when we burn the magnesium, what do you expect the mass to do? Well, it should go up because it's going to bond with oxygen in the air. And as you could probably imagine, that's how we're going to find the mass of oxygen. You're going to take the before mass, burn it. You now have magnesium oxide, and you're going to find the difference in mass, and it's probably going to be a little bit more. So let's say the magnesium starts at 3 grams. You burn it, it's now 5 grams. How much oxygen bonded with it? 2 grams. Pretty easy. But when we burn this, we have to do it in a very controlled way for a few different reasons. If you just took this, held it in these crucible tongs, and put it in the Bunsen burner flame, it would burn very fast. Within a few seconds, you would have magnesium oxide. But the problem is magnesium oxide has very different properties as magnesium. Magnesium oxide is a kind of powdery solid, and it would kind of crumble and fall apart. It also produces an extremely bright white light, very dangerous to look at, and your teacher will certainly warn you about this. And the third reason is you wouldn't just be producing magnesium oxide. You see, when we burn this in a controlled way, it's going to react with oxygen. But if you just, let it ride, if you just burn that thing, it's going to actually bond with the other gases in the air, the most common gas in the air, which is nitrogen. Now, nitrogen normally doesn't bond with things, doesn't react with things because it's less reactive than oxygen. But if you just crank the heat on this and put this directly in there, it'll be so hot that the nitrogen will actually react too. And you're going to form magnesium nitride instead, or in addition to magnesium oxide. So again, we must do a controlled burn so that only oxygen bonds with it. Because if you burn it too fast, nitrogen will bond with it as well, which will mess up our results. It's not dangerous, it just will mess up our results. So to burn it in a controlled way, we use this, which is known as a crucible. You may have read the novel The Crucible about burning witches in Salem. Well, in a crucible in chemistry, we burn things inside this. And so you're going to probably find the mass of your lab procedure will have you find the mass of this. It'll probably have you find the mass of just the lid as well, separately. That's only because these lids have a tendency to break during labs. I shouldn't say that as if it's expected, but it has happened. And if you find the mass of the lid separately and then the lid ends up breaking on you, you can just grab a new lid, find the new mass of that, and you don't have to restart from scratch. So you're going to find the mass of the crucible, you're going to get the mass of the magnesium, and we're going to burn it. So, the ring stand goes above the Bunsen burner flame. Get that in line there. To hold the crucible above it, you use this ceramic triangle here. And the crucible is going to sit nicely on that. And of course, you're not going to, light the, well, of course, the magnesium is going to go inside the crucible. And at this point, once the burner turns on, everything's going to be way too hot to touch, so you're, of course, going to use your crucible tongs for this. So, picture this flame being on, and you're burning your magnesium. Of course, you have already found the magnesium's mass. So we're burning the magnesium, burning the magnesium, burning the magnesium. What you want to start to do is vent the top to allow air to enter, because once it consumes the oxygen inside the crucible, it's going to pretty much stop burning. So what you need to do is allow more oxygen to get inside that crucible. But what you don't want to do is just say, grab this and say, go ahead, breathe, take all the oxygen you want. Because remember, I said before, we need a controlled, steady burn. And if you do that, you're going to get a big rush of oxygen, which is going to cause your magnesium to flare up and light, which we don't want. When you see the magnesium light up, what it means is it's burning very fast and in an uncontrolled way. And I don't mean like it's going to start a fire in the lab. I mean it's burning so fast it's going to bond with nitrogen. And something else will happen too. It'll start billowing this white smoke, and that white smoke is little solid particulates of magnesium oxide that are escaping into the air. And if they're escaping into the air, I mean, look, it's not harmful. They're going into the ventilation system, but that's your lab data escaping through the vents. So again, what we want is a controlled opening of the crucible to allow a little bit of oxygen in, but not enough to make it kind of flare up and light up. So the technique we'll use is kind of like opening it and peeking inside, okay? Now keep in mind, it's going to be very hot, so you're not going to stick your face right in the Bunsen burner flame, but with your goggles on, of course, you're going to grip the lid, open it a little bit, look inside, and you're going to see the magnesium inside. Don't do what I just did. The magnesium inside is probably going to start out as like an orange, and as you keep looking at it, it's going to get brighter and brighter, and then as soon as it starts to turn white, you close it up again. Okay? Didn't break, but as you can see, these things can break if they drop from a sufficient height, so we'll be careful with that. So again, what you're doing is you kind of peek inside, and as soon as you see that white flame start to kind of like open up, you cover it back up. Okay? You let it burn for another 30 seconds or so, or a minute, follow your teacher's instructions, and then you're going to peek again. So you peek, and you close it. And you're going to repeat this for 5-10 minutes, depending on what your teacher tells you. Certain pieces will just happen to burn faster than others. But basically, you want to do this until the entire piece of magnesium ends up coated in magnesium oxide, which you'll be able to tell because it's a kind of white, powdery color on the outside. Okay? Now, let's say you do this for 10 minutes or so. You're confident that you have the entire piece as magnesium oxide. Here's what we're going to do. Kill the Bunsen burner flame, and we wait. And you're going to take the crucible and transfer it to this ceramic mesh. You're never going to put this directly on the lab tables because it'll burn them. So this carefully goes onto the ceramic mesh. The crucible goes onto the ceramic mesh, and now you're just going to allow it to cool down. You don't want to put it directly on the balance when it's super hot because it'll break the balance. So you want to give it time to cool down. What we're going to do is allow some time to pass. And then once it's finally cool, you're going to put it on the balance and you're going to find the new mass. Now, what should the mass have done? Well, it should have gone up. Okay? So, what we want to do is make sure that we're actually done. Because even though the outside of this should appear to be magnesium oxide, for all we know, maybe the inside of it didn't fully react. So we're going to burn it again. And we're going to do this concept called heating to constant mass. Think about it. Imagine it was 80% done, but not 100%. And by done, I mean turned to magnesium oxide. If 80% of the magnesium turned to magnesium oxide and 20% of it was still magnesium, that means that when you burn it again, the mass should actually go up. So if you burn it again and the mass goes up, that tells you that you weren't done the first time. And in fact, you're going to even run a third burn to make sure. Because once you burn it twice in a row and the mass doesn't change, that tells you that you're sufficiently done. And we refer to this, again, this lab technique as burning to constant mass, or heating to constant mass, I should say. Heating to constant mass. Okay, so let's assume we're now done with the lab. We've heated our crucible, so the mass is not changing, which gives us confidence that the entire piece of magnesium is now magnesium oxide. Let's assume some sample data here, and in fact, I'm going to run sample data not with magnesium, with a different metal, because I don't want to confuse you for your actual lab calculations. Okay, so here's some sample data I made up. Well, you can't just make up random numbers for this. You have to actually kind of work backwards from an answer that works, which is kind of a good technique to study. Make up your own examples that work. But anyway, let's say the mass of the empty crucible was 26.29 grams, and the mass of the lid was this. Now, I think I can't remember if I mentioned this or not, but the lid, you only find the mass of the lid so that if the lid breaks in the middle of the lab, you don't need to restart from scratch. So in this case, this is extra information that we don't actually need. Mass of crucible plus lid plus copper before burning. Okay. What did I tell you we need in order to solve the lab? Two things. You need the mass of the magnesium, or in this case copper, and the mass of the oxygen that bonds with it. Okay? Those are the two things you need. Mass of the metal, mass of the oxygen. Look at these first things here. Can I find the mass of the metal? Yeah? Mass of empty crucible plus lid is this. Mass of crucible plus lid plus copper is this. Easy. You do this minus this, that's the mass of the copper. So, 28.65 grams, let me write up here, 28.65 grams minus 26.29 grams. 6.29 gives us 2.36 grams. 2.36 grams is the mass of the copper. Now, of course, when you do this, it's going to be magnesium. Okay. Now, I said mass of crucible plus copper question mark oxide. What I meant here was we don't know what copper's charge is going to be, so I don't actually know what it's going to be called, but notice copper oxide, that's going to be after you burn it. And notice it went from this to that. It went from 28.65 to 29.84. It went up a little bit, which makes sense because oxygen now bonded to it. So, remember the two things we need. Mass of the metal, mass of oxygen. Not mass of the metal oxide. We need the mass of the oxygen itself. What's the mass of the oxygen itself? Think about it for a second. What's the mass of the oxygen? Well, it's the added mass. It's whatever mass was added to it. So we're going to say 29.84 grams minus 28.65 grams. That's the added mass, which is our oxygen. 29.84 minus 28.65 gives us 1.19 grams, and that's going to be our mass of oxygen. 1.19 grams of oxygen. Why don't you take it from here, solve this out, pause the video, see if you can work out the empirical formula. All right, I'll finish it out here. So copper is 63.55 grams per mole, so 1 mole over 55.5. Nope, 63.55. And I lost my color there. Okay, 63.55 grams. Oxygen, 1 mole over 16.00 grams. 2.36 over 63.55 gives us 0.0371 moles of copper. 1.19 over 16 gives us 0.0744 moles of oxygen. We're going to look for a pattern here. I almost boxed it as if it's a final answer. We're looking for a pattern. It looks like 2 to 1 to me. Let's double check. So to do that, you divide both of them by the smaller number. So divided by 0.0371, divided by 0.0371. This obviously equals 1. And this looks like 2. And 2.00539, close enough to 2 that we can, with confidence, say that that is 2. So we have 1 mole of copper, 2 moles of oxygen. Our empirical formula is going to be CuO2. That's the answer. And of course we can name this. 2 oxygens bonded to that copper. That copper must have a charge of 4+. That's going to be copper 4 oxide. So that's how we run those sample calculations from the lab. Make sure you ask your teacher if you have any questions about the lab, and make sure you stay safe during the lab. Don't forget, everything is going to stay hot for a very long time. Let's avoid burns. You don't touch anything that's been in that Bunsen burner flame. Good luck.